Hello guys, today we're going to go over finding the area under the curve of a normal distribution curve and also how to assess normality. Are we looking at a normal distribution or not? So first, to begin, in order to find the area below the normal distribution curve, we actually have to use z-score and the z-score table provided in the back of the book or just any normal z-score table. Now, in order to find the z-score, remember, we have to use our target value minus the average divided by standard deviation. Now, that's going to give you a particular value, for example, 0.952 or 1.296. So once you do these operations, you might get values that range usually from +3 to -3, normally, almost all the time. You're going to get a value from +3 to -3. Now, what you do is you go to the z-score table. The table has a column and has a row. In the column, you're going to see different numbers like -3, -2, -1, -0, 0, 1, 2, 3. And you're going to say, hold on, -0? Really? -0 is not a number. You'll see how this works in a second. And here on the rows, you're going to have different values: 0.9, 0.8, 0.7, 0.6, 0.5, 0.4, 0.3, 0.2, 0.1, etc., etc. A whole bunch of different values. So what you have to do is you have to take the given z-score and you pretty much focus on the first three numbers most of the part. Either the first two or the first three, depending on how good your table is. In this case, since I only have one decimal number, I'm only going to use the whole number and the decimal part. So what you do is you look at the whole number and we're going to focus on that particular row. So I'm going to focus on the 0 and then 0.9. When these true values cross in a table, it's going to give me a value there, which is a proportion of the 100%. So 0.1 would be, this value corresponds to 10% of all measurements. Or if you get a number that's like 0.65 there, that's 65% of all measurements lie under that value. So if I have a curve, and let's say that the value you're given is here, and you get the z-score value, that means that 65% of all measurements are under the value that you plugged in to get your z-score. There is a -0 pretty much because there's also a chance you get -0.125. So in this case, you wouldn't use the +0, you use the -0 and then go to the +1, to the 0.1 here. So where they cross, again, you'll get the proportion. Now, one thing to keep in mind, you're gonna have to, let's say I have a curve, and let's say my mean is 6, and my standard deviation is 2. Let's say, for example, I plug in a target value of 6.5 and I get a z-score of, I don't know, 1.1 something. And when you find the value in the z-score table, you end up with maybe a number like 0.7. That means that 70% of all measurements would fall below that target value of 6.5 that you use to find the z-score. So again, I choose a target value, plug it into the z-score formula, I get an actual z-score, and using the table, I find the proportion that lies under that particular value. Now, there is a little wording that might get there's wording that can get a little tricky. Remember, at most means it's that value or less. At least it's that value or more. You must, at most, you can be 18 years to join this club. That means you have to be 18 or less. At least you have to be at least 15 years to apply for a driver's permit. That's 15 or more. So even though you hear the word least and you think less, that at least sets a lower bound, and it means that it's from that value onward. So at most, at least, more than, less than, in between. And one thing to note, let's say for example, again, I have my z-score, my mean is 10 and my standard deviation is 1. Let's say I ask you, what percentage of this normally distributed population lies between 8.5 and 10.9? How do I find the area that is between 8.5 and 10.9? So this area, you have to do the following. You find the z-score for 8.5. You look at the table to find the proportion of people that lie under that measurement. So let's say this gives you, 30%, so to speak. And then you find the z-score for 10.9. You look at the z-score table and you find the area under that value, which means everything under 10.9. Let's say you get a value of, 75%. What you do is you subtract the areas. So 75 minus 30, that means that between these two values, you have more or less 45%. You have to subtract the areas. You cannot subtract these values and find the z-score of the resultant value in the table. You cannot subtract z-scores because, again, you're going to get a wonky answer. What you have to do is find the area under the small one, find the area under the larger value, and then find the difference. Think of it like in a linear fashion. You have a line, only the difference is here, a line is simpler, but we have an area that changes based on the position. So it's not like a direct line. But let's say, for example, from here to here, I have 3, and from here to here, I have 8. Between these two values, I would have 5. The same concept applies. You find the area from the lower value to the minimum, the area from the higher value to the minimum, and that difference of area is the area contained within those two intervals under the normal distribution curve. Now, the other subject we're going to go over, one thing, there's also something called, just give me a second. Again, theoretically, you can use this to calculate the area under the curve. I don't see it as necessary if you're doing the z-score values. It's called the standard normal distribution. The standard normal distribution is pretty much the normal distribution curve, only we have a mean of 0 and a standard deviation of 1. Why can we force another normal bell curve distribution, which has different numbers, into this exact same shape? Because remember, in order to find the z-score, you subtract a value from the mean, and you also divide by a constant. You're subtracting a constant and dividing by a constant. So neither of these changes the actual shape of the graph. So you could find the z-score using the standard normal distribution. Just know that exists, but don't worry. Find the z-score normally, use the table, and you're done. Now, the next thing, which was pretty cool, and it's very useful, is the normal probability plot. Now, it might sound confusing. It's not. Now, the normal probability plot is a scatter plot of ordered pairs in which the x is the data value or the measurement, and the y is the expected z-score from that one value. So again, you have an x and a y in an ordered pair. The x is the data measurement, and the y is the z-score given that data measurement. So again, I'm not gonna ask you, probably, I hope not, that you have to draw a normal probability plot, but they will probably ask you to evaluate, is this normal? And what happens is, when you turn this into measurements and their expected z-score in a scatter plot, again, the x is the actual measurement and the y is the z-score you get, you'll notice a couple of things. Sometimes they might line up more or less like a straight line. Sometimes they might line up like different parent functions. Other times they might not have any association. And the fact of the matter is, while looking at a graph, the more it resembles a linear function, the more normal the distribution of these data sets will actually be. So the straighter the line of the normal probability plot, the better or more normal the distribution will be. This might be a little wonky off to one side. This might have some crazy distribution. So again, the more linear the data or the scatter plot looks, the more normal the data will be distributed. And remember, people say, Profe, pero again, this is a straight line. How is this a curve? I mean, curve, straight line makes no sense. Remember, you're not plotting a curve onto a two-dimensional XY plot. You're just plotting two values, an X, which is a measurement, and a Y, which is a z-score, which when you combine those two in a normal distribution, they should line up. In a normal distribution, they will line up. So quickly looking at a data graph, or at a normal probability plot, you can see, yeah, this should have a normal distribution. This has absolutely not a normal distribution. This has a somewhat normal distribution, but it's skewed one way or the other. We'll go into that later. So that's pretty much it for today. Have a great day.